Hello, we are the Laser Beam Characterizer Group for Senior Design Fall 2025 to 2026, Group 3. I am Zachary Andreessen, photonics student and electrical engineer,
I'm Thomas Cunningham, an electrical engineering student.
I'm Lindsay Smith, a computer engineering student.
and we are sponsored by Lockheed Martin. For our motivation for this project, our sponsor does a lot of motivation. It does a lot of model matching. And so it is necessary to know many properties of a laser in order to match a model that we have for our laser system with the system that we built. And so in order to do this, we need to know the laser's wavelength, polarization, divergence, and beam quality. And so our system automates this data collection process. So for our basic goals and objectives, we want to measure polarization, wavelength, M squared factor, and divergence, as well as accommodate for a broad range of input powers, input beam sizes, wavelengths, and if possible, to measure the beam waist size and location. So to measure polarization, we use a rotating quarter wave plate method, where we rotate a quarter wave plate and then have a fixed linear polarizer and then measure power as a function of that quarter wave plate angle. From this, we can get the Stokes parameters. To measure the wavelength, we use a simple Michelson interferometer using a beam splitter to split the beam into two arms to create an interference pattern, which we can read with a photodetector. To measure the M squared factor, we have a beam profiler where we have a scanning knife edge to measure the intensity distribution of the beam. And we use a lens to focus the beam to measure several points along the path of the beam. We need to know the waist and divergence, and from this we can calculate the M squared factor. To measure the divergence, we use the same knife edge scan method to measure the beam width, but not at several points, but only at the focal point of the lens. And from this, we can calculate the divergence of the beam. Here's a rough layout of our optical schematic. We have two irises at the bottom, which the user can use to align their laser. And then there are the three systems. The quarter wave plate linear polarizer comprise the polar emitter. The lens is an 812 millimeter focal length lens. And the beam sampler after that will split the beam to go to the Michelson interferometer and to the beam profiling system. A system comprises two layers. The top layer is a Michelson interferometer, as you can see on the left, and the bottom layer comprises the polarimeter and beam scanning system. Here's the full system stacked on top of each other. You can see the two irises on the bottom, as well as the polarimeter focusing lens as it goes on the bottom layer, and then the interferometer on the top. For our specifications, we have a 1.2 to 2.1 micron wavelength range, as well as a maximum power between 1 to 10 watts, minimum power of 1 to 50 milliwatts, and beam diameter between 4 and 35 millimeters. For our measurement parameters, we are measuring the Stokes parameters within 5%, wavelength within a nanometer, M squared factor within 0.1, beam divergence within 10 microradians, and a total power measurement of 5% error.
The electrical hardware is very simple for the system. We have our STM32 microcontroller. Being at the center of it is powered, all this whole system is powered from a 12-volt DC wall adapter, which is split into 5 volts and 3.3 volts via switching regulators. The STM interfaces with our stepper motor drivers and DC motor driver to control the motion. We have the power meter TIAs coming in through analog channels, and all of this data will be processed and packaged and sent to the PC for further processing and data presentation. Of the many motors, we have NEMA 17 and NEMA 13 stepper motors, which are one is used for the quarter wave plate rotation, providing really good angle resolution, and the other two are used for linear translation with a ball screw system. We have two DC motors with encoders. These provide a constant and controllable speed using a simple feedback loop inside of the controller for our beam profiling knife edge test.
For our optics hardware selection, we chose this power meter head from Thor Labs. The main advantages of this is that it has a 5 millimeter input aperture, which is much better than most photodiodes, as well as a really low responsivity. And this made it really ideal for our application. For our beam splitter, we chose this beam splitter from Thor Labs. It spans our entire wavelength range, as well as has a very good 50-50 split across the wavelengths we want to measure.
For the MCU selection, we chose the STM32 over the ESP32, mainly for its superior ADC, which is more accurate and linear. And then another advantage of it is the native motor driving software, which is important since we have multiple motors for this project.
The MCU design on the main PCB is centered around the STM32 microcontroller, and branching out from that, we have um, our motors and photodiode pins. You can see in the yellow is the circuitry for the motor drivers. With optocouplers, we have on the cyan, some on the right corner, the DC motor driver connectors. The green is where our regulators will connect, and the pink is the TIA input pins. Here is that laid out on our physical board with the stepper motor drivers and regulators already on the board. The stepper motor drivers were custom made, but the schematic was taken directly from the DRV 8825 datasheet by Texas Instruments.
For a photodiode, for the Michelson interferometer, we use a simple extended InGaAs photodiode and an OPA 129 op amp, which is known for low noise applications. For the power meter head from Thor Labs, we integrated this into a custom-made variable gain TIA, which has 4 stages, each with a gain of 10x the previous stage. And we use the ADG 1211 voltage controlled switch to adjust the gain in the feedback of the TIA.
For the software selection, on the embedded firmware side, we chose embedded C as a programming language for precise ADC timing and deterministic behavior. And the main reason of using Python for our PC GUI is for it allows for a scalable GUI for system control and data analysis. The software flowchart for embedded firmware is the STM32 peripherals of ADC DMA timers. And then the firmware will wait for a measurement plan selection from the GUI. That selected plan configures the scan parameters and calibration, and then it goes through a closed loop measurement process of motion control, sensor data acquisition, and real-time signal processing. And then that process data is streamed to the GUI for visualization, and any final beam parameters are computed and system returns to idle. The GUI software flowchart is once the application is started, it initializes the GUI and loads up defaults, and it should automatically search for a serial communication port to attempt connection to. And if it's a seeds, the main screen is shown, and you should be able to select a measurement system or automatically run all measurement systems in a certain order. And then once that measurement system is selected, the GUI sends start commands to the measurement workflow scripts on the STM32. And that data collected from the STM is sent back to the GUI for data processing.
Throughout this project, Zach has been the project lead on making sure that we are getting things done on time. He also is responsible for all of the photonics engineering in the project, as well as the TIA and power meter um, circuit boards. I'm responsible for all of I'm responsible for all the other circuit board designs, as well as making sure the motors and any mechanical parts run smooth. And Lindsay is in control of all of the software and firmware.